welcome back to iolite's Python for LA-ICP-MS course. Today we turn our attention to writing custom imaging inspectors. A brief outline for today's lesson is shown here. We will start by talking about what an imaging inspector is and why you might want to create your own. We will talk about what the requirements are for inspector scripts and which objects will be available for you to use. In doing so, we'll also touch on some new API features that may be useful beyond just imaging inspectors. Then, like the weeks that came before, we'll have a live coding example and an assignment. To begin, let's have a look at some of the built-in imaging inspectors so you can see where to find them and how they work. In iolite, when we come to the Imaging tab, you'll find that there is a button in the top right corner that's labeled Inspect. If we click that, a panel will pop out on the right-hand side, and in the top part, you have some controls to change what you're inspecting, and in the bottom part, you have a list of inspectors. So the three different types of, or the three different modes of inspection are loop, region of interest, and profile. When you're in loop mode, the thing that you're inspecting is whatever is under the mouse on the image. And you can change the geometry of that inspector, so we could change it to a rectangle, and we could change the dimensions and the rotation and so on. Then we've got region of interest, and this could allow you to create regions of interest from polygons or different things like criteria. And then we have profiles. You can also create a region of interest from what's under the loop. So for example, if I liked what was here under this square, I could control click and create a region of interest. And now I've got a region of interest corresponding to that loop position. Now, we can also add inspectors as a way to visualize what's happening with the data under the loop or for the different regions of interest or profiles that we have selected. So we've got this add inspector button, and then there's a series of built-in inspectors. And then down below the line, you've got this Python menu and then your Python-based inspectors. So just for an example, I'm going to pop in this rare earth element inspector. And now you can see that as I mouse over the image, I get a chondrite normalized rare earth element plot corresponding to the data that's under the mouse. Now, if I were to create a region of interest like so, I could then select that region of interest, and that's what's plotted now in the inspector. So when I'm in loop mode, it's what's under the mouse. When I'm in region of interest tab, it's what's under, it's the region of interest that I have selected. And if I were in profile mode, I would need to create a profile. Oops. So I could do that by clicking add and then defining the vertices of the profile, giving it a name, and then selecting that profile. Obviously those slices are much too big, so I could change the dimensions of the slices. And now I've got a whole bunch of rare earth element patterns corresponding to each slice of the profile. Okay, now when it comes to inspectors, you can add a bunch of them. So I could add in additional inspectors here. Let's see, put in a few of them. We can also change the size of them using this tool in here, and to get them all to fit. And now I could go back to the loop and I can have them all update simultaneously. Maybe I should change this to be something more useful, say barium. Yeah. Okay. Now typically an inspector, or most commonly, they consist of a plot and a few controls to change the settings for that plot. Now you'll also notice that they each have this little hamburger menu in the top right, and if you click that, you can undock a region of interest so that it comes out of that thing and you can make it bigger or smaller and it stays on top. We can dock it back in. You can also change the size of it, as I was also already showing, and you can close it. Now, when it comes to Python-based inspectors, you can use this Python menu here. So I've already got a few scripts in here, but if you wanted to create a new one, you could come and use this add menu item. When you do that, it creates this little dialog where you give it a name, and then you can base it off of one of the built-ins or any of your previous Python-based imaging scripts. And when you do that, it simply copies the template that you chose to your user scripts folder. And so typically that's documents /iolite /scripts /imaging inspectors. And this will be a folder containing all of your imaging inspector scripts. And as you change those, every time you access this menu, it'll be populated with the scripts that are in that folder. Now, let's see. If I were to add a Python-based inspector, so I'm going to add this assign1.py, you'll notice that there's a few more controls now in the top right. One of them is to reload the script, and the other is to edit it. So why write your own imaging inspector? Well, we can only really focus on one or maybe a few things at a time, so noticing how data are changing between multiple images simultaneously can be quite difficult. Imaging inspectors allow you to use your knowledge of the science behind your sample to distill complex data into something we can immediately recognize. For example, iolite plugins like VisualAge and Review are popular for time-resolved data in part because they make it easy to understand how some complex and interrelated data change with time. Imaging inspectors just apply that idea spatially. Now we know what an inspector does and are motivated to create one, but before we get to that, we need to talk about what are the requirements for an inspector script. So an inspector script does not require any specific metadata. It requires two functions to be defined, one called create, which returns a widget to put into that inspectors list, and the other is update, and that will be called whenever the loop changes its position or geometry, or the selection of a region of interest or profile happens in those tables. The objects available to you in the script are the usual data and iolog, but now we have two new things. One is inspector, so there's an inspector object and an imaging object. So we'll talk a little bit more about those new ones now. So the inspector object, the main function that you'll be using with the inspector object is the ROIs, so that just returns the list of regions of interest that the inspector should use. Then we have a series of functions related to the settings and the color that should be used for a given region of interest. Now, a region of interest in Python is represented by this ROI Pi interface type. And so if you have a region of interest, you have a few functions available to you. One is the name, that just gets the name of the region. Most important probably is the mask. So we'll talk a little bit more about the mask in a second. And then we have the centroid, which is the physical coordinates of the center of the region of interest and number of points and polygons. So what is a region of interest? Let's talk a little bit more about that now. So a region of interest can be represented by a series of polygons or be disjoint, what we call disjoint. So that just means that the time slices contributing to the region can't really be represented easily by geometric shapes. So for example, when you create a region of interest using criteria, we can't really say like that this is a circle at this coordinate and a square at this coordinate. It's just a series of indices that match. So a region of interest has a mask that records which indices of the channel data contribute to it. That's why that mask is so important, because that's how we can get the stats for a region of interest. In both cases, so whether a region of interest is based on geometry or is disjoint, you can get the individual measurements contributing to an ROI by doing something like channel data and then indexing it by ROI.mask. And so if you wanted to get the mean of a region of interest, you can use that and then just do .mean, or if you wanted the standard deviation, .std, or if you wanted the median, I think you can also do .median. So profiles are composed of regions of interest along a path that are determined by the slice width and height. So you can apply the same sort of concepts to profiles. And now the value of inspector.roi depends on which inspection tab you're on. So if you're on the loop tab, then the inspector.roi will contain a special ROI that represents the loop geometry. If you're on the region of interest tab, then you get a list of whichever ROI are selected. And in the profile tab, it will be the ROI of the selected profiles. So here's just an example of this idea that some regions of interest could be represented geometrically. So on the left here, we have a bunch of different ROIs that are just circles that were probably created with the loop. And then on the right, we have a disjoint ROI that was created from criteria to pick out these different appetite. Okay, so there's a few other features in the imaging API that you may come across as well, and we'll use a few of today. So we also have the imaging object, and this is a more general interface to the to imaging. So you can get a list of all of the ROIs, not just the ones that are passed to the inspector, which can be useful if you wanted to, for example, if you wanted to plot in your inspector all of the regions of interest, but then overlay where the loop is relative to that. Some other ones that we will use later are the pix map, so that'll get the actual image that has been generated, so the actual image data for a particular image. And then we've got these physical minimum and physical size that can be useful as well. And outside of imaging inspectors, another useful one is this matrix. So that's a way to get the actual numerical data that goes into generating an image in Python. So if you were to get a profile, you would get a profile pi interface object, and this is similar to the ROI pi interface object. If you have one of these profiles, you've got functions for the name and the section height and width and vertices and so on. But most importantly, you've got this function to get the ROIs that correspond to each section or slice of the profile. And then I think lastly, we have the iolite image pi interface. So this is if we were to do imaging.image to actually get one of the images from imaging, we could then get the name and channel and group and so on that are associated with it. The data function here returns the matrix that was used to make the image. And then we have a series of functions to get and set different properties of the image, like the scale type and the limits and so on. Okay, one more API thing that we're going to talk about, because we'll use it later, is this data.elements dict that's available as part of the data object. So this is a dict with elements as keys and another dict of element properties as the values. So for example, if we did data.elements and provided the key of U for uranium, you would get, or you would see a dict of a whole bunch of information related to uranium. So you can get CI would be the chondrite concentration of uranium, more muck. You can get condensation temperatures, a whole bunch of different things, ionization energies, boiling points, melting points, and then there's also the isotopes, and the isotopes have their abundances and mass numbers and so on. So we can use this information when you're creating normalized plots. Okay, so now let's get started on some examples. The example dataset that I'm using today is an image that was collected of some manganese crusts that look pretty cool. And so I just pulled up one of the first papers that I could find on manganese crust chemistry, and I thought I'll flip through this and look at what figures and plots can be useful for manganese crust. And I came across this ternary diagram that I thought maybe we could recreate. This figure is a bit too easy, so we'll skip it. We've already got rare earth element inspectors, so we'll skip that. Again, this is just one element versus another, so we'll skip that. And then we'll do this last one here, figure 6, because it's a bit more interesting. Where we've got cobalt over zinc versus cobalt plus nickel plus copper. Okay, so the first one we're going to try is this ternary plot. So we've got iron, manganese, and cobalt plus nickel plus copper times 10 as the different corners. And so let's get started on that. So we'll come and we'll open up that, and we will go to Python add. We will call this Toth figure 1, I think. Yes, figure 1. And we'll base it on raw, I guess. And now we will get this into position. Oops. All right, getting that into position. We'll increase the font size for you guys. There. So in this template, you can see there's a big copyright statement at the top. You could modify that or change it. I'm just going to delete that and say Toth. I'm not sure what year that's from. I'll just call it Toth figure 1 by Joe Petrus, and then put my email. Now, so the two functions that we know we need are create and update, but we're not going to need a lot of this stuff, so we won't need really any settings. So to start, I'm going to remove a lot of this setting stuff because we have predefined channels that we're going to use the different parts of the ternary plot. So I'm going to remove that. I can remove that. I can remove just about all of this. So I'm going to remove that. I can remove all that. I can remove that. Now I can just do global plot. So I've got this global in the script called plot that I've created up here, which is none to start. And then I'm going to say plot equals, and then I'm going to say ternary plot, and I'll return plot. So that's already my create function defined. For now, I'm going to remove everything that's in update, and I'll just pass. But now we need to define what this ternary plot is. So for that, because we need to do some custom drawing here, we don't actually have a plotting widget that can do a ternary plot for us right off the bat. So we're going to create our own widget that can plot a ternary plot. So we'll define a class called ternary plot, and it will be a subclass of QWidget. Now, first thing we'll need is to define the constructor. And we will also need to define our paint event. Here, we'll do paint event called. Okay, so let's just have a quick look and see if that works so far. Toth figure 1. So paint event called. So you can see that paint event has been called, but we haven't actually done any drawing yet. So get rid of that and go back to our code. And now we're going to need a way to set the data and store the data that we're going to use for the ternary plots. So let's create a function here called setData, and I'll give it different vertices, and we'll also specify an array for colors. So we'll do self dot A equals A, self dot B equals B, self dot C equals C, and self dot colors equals colors. And we'll create up here self dot A, just set it to some empty lists to start. Equals empty list. Okay, so now we can probably get rid of this print statement. We know it's being called appropriately. So now we need to think about how we're going to actually draw this ternary diagram. So the way that we do some custom drawing in a Q widget is we create a painter. And the painter is going to paint on self. We need to make sure that we import Cube Painter so we can get rid of some of these things that we're not using in our imports. We'll probably end up using NumPy, so we'll leave that, but we can get rid of a bunch of this stuff because we're not using it. Cube color we may end up using eventually. Sure, we'll need that. We'll probably need cube pen eventually. All right, so we can get a rectangle corresponding to where we should paint by doing event.rect, but we don't want to draw our triangle all the way to the edges because we want a little bit of space around it to write some labels. So we'll do event.rect and then call it adjusted on that. And we'll bring it in by 20 pixels on the left and top, and then in on the right and bottom. So we'll call this our paint rect, prect. So that's what we'll do there. We can then set the pen for our painter to be white. So that'll look all right on the dark iolite background. So we're also going to need to import Qt from Qt core. And now let's see if we can draw a triangle. So the next thing we'll need is a Cube Painter path. So our triangle is going to be a Cube Painter path. And we can set the vertices to start. So we'll go triangle dot move to, and then we can use, we're going to need to do Q point F, prect dot bottom left. We're going to need to import Q point F from core. Okay, and now we do triangle dot line to, and now, so we're starting in the bottom left. So we're going to go to the top center. So the X will be, we'll do prect dot center dot X, and we'll do prect dot top. So that should move it to the top center. And then we can do triangle dot line to, now we want to go to the bottom right. So we can do Q point F prect dot bottom right. And then we want to come back to our starting position. So we'll do line to Q point F prect dot bottom left. And now we can actually draw that by doing p dot draw path triangle. So I think that should draw a triangle for us. Let's save that and go try it. Great. So now we have a triangle. I'm not sure if this will come through in the video, but if you were to see it here, you can see that the lines that are drawn are a bit jagged, and that's because we don't have, it's not anti-alias by default. So we could change that to get a nicer line. If we come in here, we could do painter set render hint qpainter dot anti-aliasing, set that to true, save that, and now that's a bit nicer. Yeah, looks good. Okay, so now we've got our triangle. The next thing we'll want to do, I guess, is write our labels. So we can do painter.draw text. And now I believe, let's see, let's pull this up again. So we want the bottom left to be iron, the bottom right to be manganese, and the other to be the metals. Okay, so we want to do draw text prect.left. So that's going to be the rectangle, the bounding rectangle of our triangle, the left side of that. But we're going to want to move a little bit further back. So we'll subtract a little bit and then do bottom. That should be all right. Let's just see if that one looks about right. Yeah, that's all right. Not sure if that'll come through in the video, but if it'll, you've got now an iron label at that vertex. Okay, well now let's add the other ones. So we want at the top the metals, so that the coordinates there will be prect.center.x, and the y will be prect.top. We'll call that cobalt plus nickel plus copper times 10. Let's have a look at that. Yeah, that's fine. So it's not centered, but that's okay. We could go back and change details like that after if we wanted to. Okay, now this one we're going to want the x to be the right side of our bounding rect for the triangle, and that'll be prect.bottom, and this is going to be the manganese. So let's have a look again at that. Right. Okay, so we're labeled now, and so the next thing to do is to actually draw the data. So let's see, we could do, so we want to get all of the data, so we could do something like this for AI, BI, CI, color, in zip self.a, self.b, self.c, self.colors. And now we need to calculate the XY coordinates of each data point, and that's a little bit tricky. So let's do the easy part first. So we can do painter.setPen and set that to the color for this data point. And then we can also do painter.drawEllipse, and we're going to draw it at, this is also a bit tricky. So where are we going to draw it? Because we need to draw it inside the bounding rec of the triangle. So we're going to do prect.left plus x. So we're going to have x. This is going to be between 0 and 1. So that'll be some fraction of the total. So we're going to go x times prect.width. But then we also need to subtract the diameter. So let's also create a parameter here called diameter, and we'll set the default to 7, say. So in here we need to subtract half of the diameter, I think. Okay, and now for the y coordinate, we'll do, so in this case, it's a little bit different because normally when you think of a graph, you start in the bottom left, but when it comes to drawing, the coordinates are in the top right. So we need to do prect.bottom minus y times prect.height minus self.diameter divided by 2. And now the next two parameters are the width and height of the ellipse. So we'll just use self.diam and self.diam. Okay, so now when it comes to the actual xy coordinates, can just kind of look this up. One formula that I looked up looked like this. 180, and that's plus vi times tan 30 times pi 180. Now we need to also bring in a few more things, so we'll go from math import sine, or wait, no, we didn't need sine, cos, tan, and pi, I think. What do we got extra there? Okay, this should be like that. Okay, so now what we're going to do is just, let's set some values here just to test this. So if we set 0, 0, and then we do 1, 0, and here we go 0, 1. Let's just have a look if that, let's have a look. Okay, that doesn't appear to be working. So what's going on? Let's have a look and see if there's any messages. QWidget has no attribute named colors. Okay, let's go back to our code. What have I done here? There we go. And wait, so sometimes we need to redo that. Self-check colors, check. All right, so we haven't actually set the colors yet, so we can do, let's see if this works. No attribute diam. Oh, I got that in the wrong spot. Okay, let's see. Right, so now I've got circular data points at each of the vertices, so I think that we're just about all set here. Well, let me just clear and make sure I'm not getting, yeah, okay, there's no errors there. Perfect. So we're on our way, so we can reset this now because we know that it's plotting appropriately. And we actually need to set that data now from our update. So what do we need here? So we can get rid of this pass. We can get the ROIs from inspector.roi. So that's going to be a list of our ROIs. Now we need to try to get the different channel data. So we'll do data.timeSeries iron 57 dot data. B is going to be 10 times data.timeSeries cobalt 59 ppm dot data plus data.timeSeries. What were they? Nickel 60 ppm data plus, and copper, I think it's 65. Okay, so that should be fine for that. And then C is going to be the manganese. So we'll do data.timeSeries manganese 55. And if there's an exception there, we will print it and return, because we're not able to update the data unless we can get all those different channels. Okay, so we'll be a bit verbose about how we do this now. So we're going to create arrays for each of the things that we're going to send to our plot, and colors as well. And then we'll iterate for each ROI in ROIs. So now we need to, so let's get the individual data for A. So we'll do np.nanmean, and then we'll do that for a.roi.mask. So that will be the mean of our ROI's A data, ignoring any nan values, any blank values. So let's do the same thing for the other ones. Now we want to normalize these, I think. So we'll do that is A data minus np.nanmin of just A divided by np.nanmax of A minus np.nanmin of A. And then we'll just repeat that for B and C. B, C, B, C, C. Okay, and now we're going to do something like this to make it so that they all sum up to 1. Okay, and now we basically just want to append that. So we'll do an.append a value, bn.append b value, cn.append c value. We can do colors.append inspector.color. Use the ROI name. And now the only thing to do is plot.setData an, bn, cn, colors. So that should call this function up here to set the data. But I think we probably also want to trigger here trigger it to repaint. So anytime we set the data now, it will repaint. Okay, let's give that a try. So nothing happening. Oh Okay, so you can see that I've got a whole bunch of these messages where it has no attribute named ROI. So I have called here, which line was that at? 64. Line 64. This should be RYS. So we'll save that. Let's just close that, create a new one. Now we're still at no. Okay, so unsupported operand. So that's coming from our exception thing here. So I've forgotten right here to put .data. Okay, so let's try that again. We'll clear this. Okay, another typo. So line 82. Let's go back. Line 82. Line 82. I mistyped that. Okay. Holy moly. Let's clear that. Okay, so unfortunately the color for that ROI isn't very good. So I don't know if this will come through, but there is a data point plotting right down there. Let me see what happens if I create a profile through here. So I'll do something like 10 to 50. Okay, so now you should be able to see some of the data plotting down in this region. So if we were to bring this up, you can see that this is similar to hydrothermal manganese crusts, and maybe it's some of the data points are coming closer to these nodule parts. Let me see what happens if I pull that out and blow it up for you. Does that help? So you can see there now, if I select the profile, you can see that so along that profile, it starts out down in the corner and then it comes up and curls around a little bit here. Okay, so there are a few things we can do to improve the visibility of those data points. And the first thing we're going to do is set the brush before we draw that triangle. So in doing so, we can set it to white, and now our triangle will be filled in white. And the other thing we can do is we can set the brush before we draw our ellipse, and that way each data point will be filled in. So now if we come back and add it in, you can see that we've got a white background for our triangle, and each of the data points are filled in, so making them much more visible. For our second example, we're going to recreate figure 6 from Toth. So just as a reminder, that is this paper here, and the figure we are trying to recreate is figure 6. So that is cobalt over zinc versus cobalt plus nickel plus copper. So to do that, we can again go to Imaging, Inspect, Add Inspector, and click to add a new Python inspector. We'll give it the name of Toth figure 6, and we'll base it off of raw.py. Now I'll open that up in code. And again, I'll replace this and just say Toth figure 6, my name, put my email. You can put whatever you want up in here. Okay, now in this case, we don't want to be able to change the X and Y channels, so we can get rid of that. We could leave in log and legend as options and settings that we can change. So we'll keep that, and here we will remove the X and Y channel, but we'll keep the log button and the legend button. So all of that is fine. The create, so already that create function is basically complete. So now we need to worry about this update function. So in this case, we need to get the zinc, cobalt, copper, and nickel. So we'll do cobalt is data.time series cobalt 59 ppm data. What do we, nickel data.time series nickel 60 data, copper 65, and zinc and then if we can't get any of those or one of those, we'll print what the exception was and return without updating. We will still get the log and legend settings from the inspector like that. We can get rid of that. We will still clear the graphs. We'll set the bottom label to be, what is it? Cobalt plus nickel plus copper. Cobalt plus nickel plus copper, ppm. We'll set the Y label to be cobalt over zinc, and we'll set the left and bottom to be logarithmic according to our setting, and we'll set the legend visible according to our setting. So now we can iterate through each region of interest that's been set on the inspector. We'll add a graph, set the name to the region of interest name. Now, how do we want to do this? So we could do it up here. So if we wanted to, we could say X equals cobalt plus nickel plus copper. Y is cobalt over zinc. And then down here, when we do X and index it by our mask and Y and index it by our mask, that should all work out. So we can do that, and we'll save that and have a look. So already this is working. So right now, the way that we have it set up, it's plotting each individual time slice rather, that contributes to this region of interest. So you can see what it's doing there as you mouse over the image. So you can see that there's a bit of a linear trend in this bit of growth here, and it's quite different there. So we could change this. Let's see. So right now that's plotting each individual data point. We could also change it so that it plots just the mean. Have a look at how that looks. So because there's only one data point, it doesn't really scale it properly. So maybe now we'll also change it so that it plots all of the regions in imaging. So not just the regions of interest that are set for the inspector, but all of the other regions of interest. So we could do something like this, and we'll take in the region, maybe the size and the color, and we will move all of this into there. And now for the inspector regions, we'll do plot ROI, R. The size will be larger to emphasize it, and we'll make it a big red one. And then for the other regions, we'll do plot ROI. We'll make these ones smaller, and these ones we'll use the inspector color for that region's name. Let's try that. So I think we've got an error. Yes, so we have not imported this cute thing. So let's go up and we'll do from iolite.qt core import cute. Let's see, we do have color. Okay, let's try that. And we'll clear this. Okay, so that's working now. but we have no other regions. So let's go and create some other regions. So we'll do, where's my, maybe we'll just go off the manganese. We'll create some regions in here. Okay, so now as we mouse over this, you can see that the plot is changing and we have our other regions, but actually it's not plotting our big red spot like we said it was. So let's have a look at that problem. Right, so we're not actually using the size and the color that we passed in, so we got to go like this. And we'll refresh it. Okay, now we've got a large red spot, and the other regions are plotted as smaller spots with their color. Now, I think what's happening now is that we have data that are plotted right at the extents. If you look very closely, you can see that there's one right here. So what I like to do to avoid that is come back here and we'll say plot.left.scale range and plot.bottom.scale range. And now that should expand it outward a little bit so we can see all the data points. All right, so that I think is pretty good. It's doing what we set out to do. Okay, for our next example, we're going to try to recreate a figure from this, from my monocle paper. So we're going to try to do, where is it? Figure 2E, where we have cerium over cerium star versus iron. So we'll try to create that plot as an inspector. So I'm just going to move that out of the way. So again, we've got our manganese crust dataset open. It's a similar dataset to what was used in that monocle paper, but a different sample. So I'm going to go add inspector, Python, add. In this case, I'll call it Petrus Fig 2. I'm going to base it off of our previous Toth Fig 6. And I will get that open somehow. There we go. So this is now going to be Petrus Fig 2. Okay, so in this case, we will keep the legend, but I think get rid of the log. We'll keep that. So we can get rid of the log button. We'll keep the legend button. We'll keep our plot. So that create function is good. We can now move to update. So in this case, we are going to need some different things. So we're going to need the cerium. We're going to need a few different rare earth elements, and we're going to need the iron. So let's first get the iron. So we know that that's going to be easy. We can just do that like that. Then we need praseodymium. Neodymium. And cerium. And we can get rid of these calculations here for X and Y. And we will keep that part. Get rid of that. We still need to clear graphs. We can change the bottom label to be iron. And we can change the Y label to be cerium over cerium star. We're not using the log settings, so we'll get rid of that bit. Now for plotting the ROI, let's see, so we still need to do an add graph. We can still set its name so that it shows up in the legend properly, but now we need to calculate the cerium. So the normalized cerium we'll do equals cerium. We'll use the region of interest mask dot mean, and now this is where we can use that data.elements dict. So I'm going to divide by data.elements. And we're going to use cerium, and then we'll get the MUQ data for that. Now we can similarly just copy that, paste it a couple of times. We're going to normalize the others as well. So we can just change these as we go. Now we can calculate cerium star, and I've just looked up some formula for this. So use that. You can use whatever you like, really. And now we are going to, for the X, we'll use iron mask dot mean. And for the Y data, we will just do cerium norm divided by cerium star. And everything else, I think, can stay. And let's give that a test. Petrus figure 2. I'm going to expand it a bit. And let's see. Okay, it's not working. Let's see. This always happens to me. So a typo for mask. Let's go back and fix that. Where did I do that? Right here. Okay. So let's have a look. Does this make sense? So we're getting fairly low. Yeah, that makes some sense. Values appear to be in about the right range. And there is this bit of a linear, there is a bit of a correlation between the two. Okay, so that's pretty much already that figure recreated. Okay, so the last example we're going to do today is a little bit different. We're going to try to create a magnifier so that in the inspector widget, we're going to have a blown up version. We're going to have a zoomed in area from around the inspector. So to do that, I will go to add inspector, Python, add. I'll call this magnifier. I'll just base it off of our previous one. Now, open that up. So this one will be called Magnifier here. You can, of course, write in whatever you want. Now, in this case, well, things will be a little bit different, you'll see. So we'll have our main widget that includes the magnifier and the settings, and then we're also going to have our magnifier widget. We're going to have a couple of different settings this time. So in this case, we're going to need a channel that we want to magnify. We'll set that by default to just be the first name in our time series list. And then we'll also take in a size parameter. So those will be our settings. This can stay the same. And now for create, we're going to want to change things a bit. So we'll have let's see, we're going to, well, not have a plot in this case, so we can do mag equals q label. Parent of widget, we can get rid of that. We're going to need to set our size policy on mag. So mag set size policy. Minimum expanding. right, our setup layout, we can keep that. We're going to change, so we don't have a legend button anymore. So now we have a, we need a channel combo box. So we'll do that equals Q combo box, give it a parent of widget. We can add items corresponding to our time series names. And we can do channel combo box dot current text changed dot connect, and we'll do the same that we've done in the past with this. Okay, and we'll set the value here, set current text to inspector dot setting channel. All right, so that's now our channel combo box. Okay, and we'll need to add that to our setup layout. So setup layout dot add widget channel combo box. For now, I'm going to just go ahead and remove all of this because we're doing something quite different this time. So we'll save that, and now we also want to add a size, so size line edit, we'll say. So size line edit equals Q line edit. Set the text to be our size setting. Well, you know what? We'll have to do this a bit differently because we don't, normally this would set our setting size to be a string of whatever was put in, so we don't actually want to do that. We're going to do, we want to be able to convert that. So we'll do a lambda here with the value, and we'll call update setting directly, setting size, but then we'll do an int on the value to make sure that it's stored as an integer. And we could also add in, no, we'll do setup layout dot add widget size line. Okay, let's just have a look. We'll also here we'll just print inspector dot settings. Let's test that and see where we're at. So magnifier, there was an error. All right. Let's clear this. So every time it's updating, it's printing our settings properly, but it wasn't able to create our widget. So there's a problem there, and it's not being printed here. Okay, so our problem is that QLineEdit is not defined. So we need to go back to our code, and we just need to import QLineEdit. Let's try that again. Plot is not defined. Okay, so we need to come back to our code. And I believe that yes, I'm adding this, but really what I want here is the magnifier, not the plot anymore. And that needs to be mag as well. Okay, so we'll save that and come back, refresh. Okay, so I've done something wrong here because the item is now a giant list. Let's see, time series name. Oh, because I'm doing add item. So what I want is add items. This has made that gigantic. We're really gonna need to close that, I think, and start fresh. Okay, so oops, I did the wrong one. What magnifier? Okay, so now we've got our channel selector and our size selector. and then a blank label down here that's nothing's on there yet. Okay, so we'll come back to our code. Just also want to do setup layout. Just insert some things, some informational things here so that we know what these settings are. Okay. So we'll add our magnifier again. Okay, so now we have channel and size. And let's see, so if I change that, let's change it to something so you can see that when I change a setting there, when it updates, it's printing out the new settings. So I think everything is working so far. All right, so now we need to go about actually zooming this thing in and doing something with our settings. That means we need to implement this update function. So we'll get rid of that print statement. We'll get rid of this pass statement. So what do we need? We need our global magnifier. And we need to get our regions of interest. So we can do inspector.ROIs. Now we can also get our channel name is setting channel. And now what we want to do is we want to try to get a pix map for that channel name, and we can do that by using the imaging object. So we can call imaging.pixmap and then the channel name. And accept exception as E. If we're unable to get that pix map, then we'll have to print our exception and return. Now, the other thing that we want to do, we want to put a couple more checks in here, because really this is only going to work, well, it works best if the ROI that's passed to it is the loop. The other regions of interest won't really make a lot of sense. So we could put in a check for that. We could say if, length of ROIs is greater than 1, is greater than 1, or length of ROIs is 0. Or ROIs 0.name is not equal to loop. Okay, so that'll check to make sure that we only have one region of interest passed to the inspector and that its name is loop. And now we can actually do a little bit better here because we have that label. We could say mag.setText could not get pixmap for channel. And here we could say mag.setText ROI is not loop. So already we could just maybe test that and see where we're at. So close that, add it back in. So could not get pixmap for channel. That's because we're not actually using that. So if I come here, so now we have ROI is not loop. So I've done something wrong in the logic there. It looks like tuple object is not callable. I see. Okay. This we just need to get rid of. So I'll close that and add it back in. Could not get pixmap for channel, so I need to set this again. ROI is not loop. Unknown C++ exception. Not loop. Abort. Okay, maybe what we should do is we should go for R in ROIs, print r.name. maybe I have it wrong here. Really, this would be more concise if I did this. It's not just one. Okay, let's save that and try that again. Okay, so it is the loop. Okay, that's just showing that because we haven't changed it to anything. So I think that it's working fine. We could, just to avoid that confusion, come down here and say, if we make it this far, we could do mag.setText, all good. And just see that shows up now. But we do need to close that and reload it. Okay, let's try this. All good. Okay, so now we've got, I think, everything we need. One more thing we need to do is get, so we can delete that now because we're not actually going to want to use the text in the end. We need to get the centroid of our region of interest. So we can do, and that will be in cell space coordinates. So we'll do ROI0.centroid. And now we need to calculate the coordinates, our XY coordinates in pixels. So we'll go px equals pixmap.width times c x imaging physical min. We'll divide that by imaging.physical size.width. And now we can do a similar thing to get the x pixels. Height. Now we need that size setting, so we'll take that as n. We'll do inspector.setting size, and now we're going to extract just a part of our pixmap. So this copy thing allows us to specify a region within the pixmap that we want to copy. So we'll do n/2 minus n/2, and then we'll do a width and height of n. Oops, we'll do pixmap equals pixmap.copy. And let's see, so now we could do mag.setPixmap and see where that gets us. Built-in Qt slot has no object. So oops, this should be like that. I'm going to fix something here. Okay, so we're making progress. Now we've got a little bit of the image extracted and being plot here. Okay, so we can do better though. The first thing I'm going to do is I'm going to come back here and I'm going to not do all of our time series names. I'm going to do imaging.image names. Let's just make sure that worked. Does kind of work. Okay. All right, so this is mostly working now. There's a couple of things that we should probably fix up. So right now it's defaulting to using the first time series name. We're going to change that similarly. we'll use the first image name, so that way getting that first pix map will work. And the other thing that I want to do is to put on some kind of crosshair just so we can highlight the actual mouse position in the image. So to do that, we can come back to our code and we'll create another function called add crosshair, and this will take in our pix map and it will return a pix map with the crosshair on it. So the way that we can do this is we need to use a QPainter. So we'll do QPainter equals QPainter, and we're going to paint on our pix map. Now we'll do painter.setPen, and we'll use a red pen with a width of 1, and we'll go with a width of 2. Let's make it a little bit heavier, and we'll do a dot line. So we'll probably need to import QPainter, so let's come up here and we'll just add in QPainter. And we can do now painter.setRender hint. This is similar to when we were doing our ternary plot. So we're going to do a set render hint. We're going to do to make it anti-aliased. And now we just need to draw 2 lines. So we can do painter.drawLine, and we'll take it at the start. The x will be pixmap.width divided by 2, and we'll start at a y of 0. We'll go to, and we'll keep the x at width at half the width, and we'll go to the pixmap height. So that'll be the vertical line. And then we can do painter.drawLine. In this case, we'll do 0, and we'll do pixmap height divided by 2 to pixmap width, and we'll keep that at height divided by 2. So that should draw the horizontal and vertical line with the pen that we've set up and the anti-aliasing. So now we can just return the pixmap, and down here we can just say add crosshair. What should I do? So I'll do PM equals add crosshair. We'll just, so let's check how that looks now. So coming back to iolite, add back in our magnifier. We have a different issue. What have I done? Oh, we've got an issue because QPen is not defined, so we need to import QPen. I think that's also in this namespace, so we'll just do that. And magnifier, QPen is not defined. Whoops. Okay, it's just because we hadn't moused over it yet. So I'm going to get rid of that printing thing. That is, where is that happening? Right here. We don't want to print that. So let's get rid of that. Okay, but you can see now our crosshair is on there. So that's looking good. Okay, so the only other thing that I want to do is I want to scale that pixmap so it actually takes up all of the space right away. So we can change this to scale to height, and we'll do the widget dot height. That means we also need to add this, I think. So let's close that, clear this, add it one last time. Oh, int object not callable. All right. So sometimes these functions are properties instead of functions. So we just need to go like that, I think. Clear this, close that, add it. Okay, there we go. So that looks like it's working now. We can scale that up. Great. So now we could add in all of the inspectors that we've created today. So we can have that magnifier, we can have our Toth figure 1, we can have our Toth figure 6, we can have our Petrus figure 2, and we might need to make some of these smaller so that they all fit. Or we could pop some out. But you can see that everything's updating as we go. Let's maybe take that one out. Now we've got our magnifier, our ternary diagram, our cerium anomaly, and our metals all inspecting this figure at the same time. We could even add in a rare earth element diagram if we wanted to. That one we might need to undock as well. Now this is a lot of information being extracted and updated from this image as you mouse over it. All right. So to summarize, there are two main functions to define for an inspector script: create and update. The create function is called when this inspector is added, and it should create and return a widget that will be inserted into the inspector area. The update function is called anytime the ROI selection changes. Now this might be from moving the loop or from changing the ROI or profile selection. And this function should update the widget. So for example, replot the data or recalculate things. You can get the ROIs to inspect from inspectors.rois, and you can get all the other ROIs from imaging.rois. So we did this in a couple of the examples that I showed you today. And you can get the individual time slices contributing to an ROI by using roi.mask to index a channel's data array. So that brings us to this week's assignment. So obviously the assignment is going to be to write your own imaging inspector. If you don't have your own imaging data, we have two example data sets that will be linked in the docs. So there's one that's a trace elements data set, it's the Gabbros map, and there's another one that has uranium lead data, and this is a map of a titanite. So option one is to create a plot spider, to create a spider diagram for some elements of your choosing. So these can be whatever you want. You can use the Gabbros dataset if you don't have your own, and you can use that data.elements dict if you want to get the different normalizing concentrations. Option two is to do a Terra-Wasserberg Concordia diagram. So you can, for this, if you don't have your own data, you can use the provided titanite dataset. And one thing to be aware of is that you can, with the iolite plot pi interface, you can do plot.add ellipse. And the parameter to that is a dictionary with x, y, and their errors and the error correlation, as well as some other things like the pen and brush and layer and line style and so on. If you have any questions about that, please just send us an email or post on the forum. And then, of course, option three is your own idea. And if you're not sure whether or not it's possible, just send us an email first. And that's everything for this week.